Okay, so for our next topic to do with scale-free behaviour, we're going to consider the whole issue of criticality. And so we'll start by considering what we mean by the critical state. Okay, so this represents something like a block of ice in a container, and we're going to warm it up so that it eventually melts and turns into water. And this is supposed to be solid blue. So this is all blue, completely solid blue, that's water, and this is completely solid ice, that's all ice. Well, as we warm it up, some of it starts to melt and we'll get little patches of water within the ice. And then we get to the point where it is exactly at the freezing point, just between ice and water. And at this point, it's said to be in the critical state. It will then, as we go beyond it, it will turn almost completely into water with just a few bits of ice floating around in it, and then it'll be completely water. But this is a mixture of ice and water. Both ice and water can exist quite happily at this temperature, which is the freezing point of water, which is 0 degrees C. So this is the critical state between the two, when it's neither mainly ice nor mainly water, but it is a mixture of both. And this is close to critical, and this is also close to critical. So there is a bit of water just starting to melt, or a bit of ice just left over. And what we find is that in these stages where it's close to criticality, there is a typical size. Here too, typical size to either the patches of water here or the patches of ice here. So, it's kind of like a normal distribution. There's a fairly average size for the water patches or the ice patches, and most of them are around that typical size. But at the critical point, there is no typical size. At this point, we've got a fractal structure. So what I've tried to show here is that we've got ice, we've got water patches in the ice patches, and then within the water patches there are patches of ice, and then within the ice there are more water patches, and that can go on down to several levels. So it's like our Sierpinski gasket. There's water within the ice and ice within the water, and water within the ice that's within the water, and so on. So we've got a fractal structure to this, so that looking out on this scale, we've got patches of water with patches of ice in them, and then if we zoom in closer here, we've got a patch of water with patches of ice with patches of water in it. So a fractal structure. And we also then find that there's a relationship between the sizes of the patches and the number of them there are. It's a power law. The number of patches of size S is proportional to S to the minus alpha, which we saw is the power law is a property of fractals. And then, as I said, back here we go to the typical size of ice patches. So there's no longer a fractal structure to it. There's just, patches of a typical size just dotted around here and there, and then it's completely gone when it's all changed to water. So this is known as critical transition. We'd say this is in the state of criticality, or the critical state, or the critical point between the two. So at the critical point, we're getting a fractal and we're getting a power law. So these three things are all related. Criticality, fractals and power laws. All those things are related. And we also might see that this is a little bit reminiscent of Zipf's idea for explaining power laws, that it's a balance between unification and diversification. So here there's a balance, exact balance between unification in solidifying into ice and diversification, melting it into water. And at the point where those two forces are exactly in balance, we get this fractal structure and power law. And this is of interest to us then, because we see power laws in socio-historical processes, we see fractals in socio-historical processes, and we suggested that, you know, the fractals that we see in things like settlement patterns are indicative of power law dynamics going on underneath them. And now we also see that it's suggestive of criticality. So they're in some kind of critical states, intermediate point between two possibilities. So this seems to be a property of human societies and of how history works, that there are power law processes, there's critical transitions, critical states, and there's fractal structures, which is why we're studying all this. Okay, now we'll consider the topic of percolation. Which is a kind of a computer model, really, of things like the critical state and critical behaviour that I've just been considering. So the idea of this is that we have a grid of cells, and we can colour those cells in with a certain probability. So if we colour in only a few, let's say we colour in only 1 in 100, let's say, then we'll just get a few coloured squares dotted around here and there. We may form a few patches, but mostly they'll be fairly isolated. On the other hand, so that's if we have a low probability of colouring them in, we just colour in 1 in 100. But if on the other hand we have a high probability of colouring them in, so we colour in, you know, let's say 99 out of 100, then almost the whole thing will be coloured in, and we'll just have a few patches that aren't coloured in, and some of those will be a bit bigger than the others, but mostly we'll get just scattered ones. And so in these two cases we tend to have a typical size to them. You know, they're mostly just going to be very small patches. There might be just a few where by chance they happen to have been coloured in next to each other. But between these two possibilities, there's the third possibility of a critical state, where we choose the probability of colouring in so that we end up with a fractal structure. So we get kind of equal colouring in of black and white, and we get patches of black of many different scales. And also we can have a patch, like here we've got a patch of black which also has patches of white within it, and if we did this on a bigger scale we might find, you know, that we then had patches of white within black, and they would have patches of black within the white within the black, and so on. So this is like the critical state that we saw with the example of ice and water. There's patches of all different sizes all mingled up together, and what we find then, this has a fractal structure. It's got smaller copies of itself within itself, and it exhibits a power law. Whereas in these cases, if we look at the sizes of the patches, they don't exhibit a power law. The size of the patch is not related to the number there are by a power law, but here the size of the patch and the number of that size are related by a power law. So that is percolation, and it's a model for thinking about critical transitions. Okay, and now we're going to consider something called self-organised criticality. So with the example of the ice turning into water and the critical state, we have to kind of make an effort to get it into the critical state. We have to get it exactly at that melting stroke freezing point of water, 0 degrees C. So we then have to keep it there to keep it in the critical state, and it might be tending to warm up because of the air in the laboratory, so we'd have to keep it back to that temperature. So it's a lot of effort to keep it in the critical state. And the same with the percolation example, that we have to choose the probability of colouring in a square just right to get the critical state where you get a fractal structure. If it's too small, we won't have the patches won't form, and if it's too big, it'll all just collapse into one great big patch. So we have to be very careful about how we choose our probability, percolation probability. But with self-organised criticality, it's about systems that tend to evolve of their own accord into the critical state, so that instead of us having to kind of make special effort to put them in the critical state, they just naturally evolve into that critical state and stay there. And the classic example of that is that of a sand pile onto which grains of sand are being dropped one at a time. As the grain of sand drops, it can just be absorbed by the pile, but as you keep dropping grains of sand, eventually a grain of sand will knock other grains of sand, and it will cause a small avalanche or slippage of the sand pile. And what you find is that if you plot the sizes of the avalanches, so you record the sizes of the avalanches and plot them, you'll find you get a power law. So as the sand drops on, most of the time it just produces a small slippage, but occasionally that slippage sets off a bit of a kind of a landslide, and you get a bit of a bigger slippage, and then very occasionally that bigger slippage becomes even bigger, and you get a huge avalanche. So it is in a critical state where you've got a power law in the response to the input, that this single grain of sand dropping can produce many small avalanches, a lesser number of medium-sized ones, and relatively few very large ones. But you can have avalanches of all sizes, and there is this power law relationship between the size and the frequency of those avalanches. And then the point about this is that if you were, say, to wipe away a lot of the sand and make it shallower, as you kept dropping sand on this, you wouldn't find a power law in the size of the avalanches. But what would happen? Most avalanches would be quite small because the slopes of the pile are relatively shallow, so there's not much scope for big avalanches. But as you keep dropping sand, it will build up and build up until you get back to this point where you can have avalanches of all different sizes, and there's a power law to them. So if you're not in the critical state, as you keep feeding the sand into the system, it will evolve towards the critical state. And similarly, if somehow you sort of made an effort to pile the sand up more steeply than that, so you sort of deliberately made it very steep, and you dropped grains of sand on it there, then here there would be a great likelihood of a big avalanche. So big avalanches would be, most avalanches would tend to be big, and the pile will quickly shed a lot of this excess sand, and it will evolve back in that direction. So whether you're below or above the critical state, you tend to evolve towards the critical state, where you then have power law behaviour to the avalanches, which you don't get in these. Now, this has been studied with real sand piles, but it's also typically studied with a computer model. In the computer model, we imagine a grid that can have certain numbers of grains of sand on each cell. So, and it can go up to 4, so it can be any number from 0 to 3. When it reaches 4, it's said to topple, and so 1 grain of sand goes to the north, south, east and west. So in this particular grid here, I've got, say, this cell is at 3, so another grain of sand dropping on there will cause it to topple. So let's imagine that happening then. So we can say, let's suppose the grain of sand is then thought to go on to any one of these cells at random. So let's suppose that it hit this cell, which had 3, so that would take it to 4. And then as it's 4, it's now going to topple, so it goes back to 0, and then we add 1, so that the grains disperse north, south, east and west. So this is 1 here, so that will go to 2. There's 1 here as well, so that goes to 2. There's 2 here, so that goes to 3. And then there's 3 here, so that's going to go to 4. But because there's 4, that's now going to topple. So that will go back to 0. And we now add 1 north, south, east and west, so that goes to 1 because that's at 0. This is 0, so this is now back to 1. This is 0, so that's 1. And then this is 3, so that's gone to 4. So this will topple 2. So that's back to 0. And we disperse north, south, east and west. So this was 0, goes back to 1. This goes up to, which is 2, goes up to 3. And this one at 3 goes to 4. So that's going to topple. And the other grain of sand just disappears off the edge of the grid. But this has got to topple now. So that's 4. So that's going to go back to 0. And we add 1 to all these. So that's that was 1 went to 2. This is also 1 went to 2, and this is 0 goes to 1. And at that point we finish. So we had an avalanche there, which I think involved 4 topplings. We toppled that one, then that toppled 2, and that caused that one to topple, and that caused this to topple. And so we, and at that point though, everything's back to below 4, and so the avalanche finishes. And so this is, as I say, a computer model of this sand pile process. And if you measure the sizes of the avalanches in terms of the number of topplings, you again find a power law, or kind of. And this phenomenon of self-organised criticality tends to emerge in situations where we've got something changing in the context of friction, or where there is some kind of driving force and then some kind of resistance to that driving force. So in this case, the sand is dropping down, so that's driving this system, adding weight to the sand pile, and there's a friction to it because the sand piles are kind of sticky, so they resist avalanches. But when it's built up too much, then there's a sudden release of the stress that's built up within the sand pile. If this were just water, where there's no real friction to its movement, as you added drops of water, it would just spread out. But because there's the friction to it, the stickiness of the sand grains, then you get this critical state and the evolution towards this critical state as you keep driving the system. So the sand pile is kind of the physical model of it. This is a kind of computerized model of self-organized criticality. But we see things in both nature and society that are reminiscent of this kind of process. And so this is the reason for us investigating it. And we might also again see something similar or reminiscent of this ideas about power laws, that there's a kind of unification and diversification. So the unification is kind of the sand dropping on, trying to put sand in this place, and the diversification is the force of gravity that's trying to dispel it. And it's the balance between these two forces that produces the power law in these sizes of avalanches at this critical state. So whether that's well, that's not a precise equation, but it's just suggesting that whole idea of a balance between two forces, which was part of Zith's idea to explain power laws, seems to be happening here too. There's a driving force to it, and there's a frictional resistance to that force, and it's the balance between them that produces the critical state with the power law to it. Okay, so now let's just consider some examples of this. Okay, so we're going to consider two examples from the natural world, and then a couple of examples from history and society. And you might think, well, why are we studying things in the natural world? They provide us with a good sort of mental picture of what's going on in self-organised criticality. They help bring out some of the issues that might help us when we try to think about the extent to which self-organised criticality might explain some of the phenomena we observe in history and society. So we'll start with earthquakes. Okay, so as we know, earthquakes occur in places where tectonic plates are sliding against each other. So, one is moving relative to the other. And as this is trying to move over that tectonic plate, there's friction between them because, they're kind of jagged on all scales. And so there's a resistance to the movement of the tectonic plate. And so stress builds up as this plate is trying to move. Stress is building up along the fault line, and then eventually it's built up enough that there's a slip. And what I've shown here is that there's just a slip in a particular part of the plate here. So this has slipped past, that part has slipped past this bit. So the stress was very high there, and it's now been released. But although that has now slipped past and released stress there, it's created more stress on this because these are now kind of being stretched apart a bit. So the release of stress here has transferred stress elsewhere down the fault. And that transfer of stress further down the fault might cause that bit to slip as well. And if it does, then it will put stress on the next part of the fault. And often enough, the stress after a short while will be absorbed. But occasionally the plate gets it into get the plates get themselves into the situation where the stress is just distributed along the fault, so that you get a domino effect and you can get a huge earthquake. And it's very like the sand pile, where there's this constant dripping of the sand onto the pile, and sometimes, or most of the time, it's kind of absorbed into the pile, or there's maybe a small slippage, but it builds itself up to the point where it can have just one grain of sand can knock off a whole chain of events, and a large slippage occurs, as we saw in the computerized model example, where you've got a grid. Where we dropped the grain, imaginary grain, on a particular cell, it caused a chain reaction of 4 cells, and after that it petered out. There were places where we might have dropped the sand on that grid that just petered out after 1 topple. But if we kept playing that, we could eventually find the whole grid gets itself into the situation where 1 grain will topple, a chain reaction that goes on for a long time. So this earthquake example is exactly the same kind of principle as the sand pile example, that there's this constant inputting force, the sliding of the tectonic plates, and there's a friction, and that causes there to be a power law in the slippages that occur. Because I should perhaps have said that people do find power laws in the severity of earthquakes, and so this sort of idea of what's going on based on self-organised criticality is a possible explanation for it. Then another example is, again from nature, biological extinctions. So we know that in nature species are going extinct all the time. It's a natural phenomenon. Species seem to have a typical lifetime of about 1 million years. So species are going extinct all the time, and when a species goes extinct, it potentially puts stress on the things that used to eat that species. And so it might be that as a particular species goes extinct, the thing that preyed on that also goes extinct, because it's just lost its food supply. And then that will cause problems for the things that preyed upon that species. And so again, we've got the situation where we can kick off a whole chain reaction, and a whole domino effect occurs, and many species go extinct. But most of the time it will just be one species goes extinct, just as most of the time when the sand grain drops on it, it's just it's either absorbed or causes a very, very small slippage. So most of the time the species going extinct is absorbed, but the biosphere, perhaps like the sand pile, evolves into that critical state where you can get these big avalanches of extinctions. It's one species going extinct, the condition of all the other species is such that one species going extinct causes problems, that causes problems, that causes problems, that causes problems, and everything, or a very large number, go extinct. Then to take a now a socio-historical example is economic crashes. So it's a very similar idea and argument that businesses are going bankrupt all the time. An idea has run out of steam, or maybe businesses just close down because the the proprietors have reached retirement age or whatever. So businesses are going out of business all the time, and most of the time that will just be absorbed. But occasionally a particular business going out of business may cause problems for its suppliers. You know, they depended on it for custom, and so might just cause another business to go bankrupt, and then the bankruptcy of that business then affects other businesses. And so yet again, like the biological extinctions, you could possibly kick off a whole chain reaction that causes a large number of businesses to go extinct, and you end up, or to go bankrupt, and you end up with a huge economic crash. So again, we've got a constant input of the tendency of businesses to close down, and most of the time it's absorbed, but occasionally it can trigger a huge chain reaction. And if it's self-organised criticality, we would expect a power law, and indeed, you know, there are arguments that there are power laws in the sizes or the frequency of economic crashes. And then another possible example is wars. So a war is a response to social stress. There are issues at stake, and the war is fought until those issues have been resolved one way or the other. So a war is a release of the social stress. But it may be that, similar to these things, that when the war takes place, it releases stress at that point, but it only creates other issues elsewhere, or increases social stress elsewhere in the system. And so again, you may have that most of the time you have small conflicts, but that may evolve the whole social system into the state where it's primed for stress here to trigger stress there, to trigger stress there, and that you have a general war, and so you get a huge war. So most of the time you'll get small ones, but because those issues can be resolved relatively easily and absorbed, but sometimes it will trigger off a much more general cataclysm. So, but now all of these are kind of speculative. I mean, they're not necessarily accepted, even with this earthquake example, that that these are, you know, is genuinely examples of self-organised criticality. But having that model of self-organised criticality, it certainly helps us think about what issues might lie behind this. So the jury may still be out on whether it is a good model of any of these, but it's certainly a useful tool for thought and worthy of further investigation. And there are two key points that come out of it if self-organised criticality does apply, which is firstly that big events don't have to have big causes. So you know, in the sand pile, the cause is constant. It's just one grain of sand at a time. But we sometimes get small avalanches, but we sometimes get huge ones. But the huge ones aren't caused by a huge grain of sand. They're caused by the same size grain of sand as any other avalanche. The big avalanches are caused by the properties of the sand pile itself, by the properties of the system, that it's kind of got itself into that configuration where the sand grains are arranged in just the way that when one comes in, it's going to trigger you know, a whole range of knock-on effects. Well, the same could be true, for example, with biological extinctions. We've got the constant background of species going extinct, and when we have a huge extinction event like the extinction of the dinosaurs that wiped out, you know, a large number of species all at once, it may be that it was just caused by one species going extinct, and in that particular case the biosphere had evolved itself into the state where that could trigger this chain reaction, and the whole dinosaur, all the dinosaur species all disappeared. So you know, the common explanation for the disappearance of the dinosaurs is that a comet hit the Earth and you know, caused a gas clouds that blotted out the sunlight or what have you, and destroyed all the dinosaurs, sort of by that effect. But it could be that, but it doesn't necessarily have to be that. The big event like the dinosaur extinction could be caused by the same kinds of small events that cause less of extinctions if self-organized criticality applies. So the lesson is that big events do not have to have big causes if self-organized criticality is at work. This same with the economic crashes, that something like the collapse of Rome could be just a larger avalanche within the system that's the same as the local corner shop going out of business. Most of the time, the corner shop going out of business, it stops there. But occasionally, it sets off such a chain of reaction that you get the collapse of the Roman Empire, let's say. So that's one of the key points. Big events do not have to have big causes if self-organized criticality is applying. And the second key point also is that kind of trying to prevent it is unlikely to work, because the critical state is a robust state. The system evolves towards that critical state where you can get small, medium or huge avalanches. So we saw with the sand pile that if you get rid of a lot of the sand and make it shallower, it will just evolve back to this critical state where the slope, the critical slope, you can call that, it would just evolve back towards the critical slope where you can get these huge avalanches again. You get this power law. Or you could, try and erect a barrier on the sand pile, to stop the avalanches, so that they'll as the sand rolls down here, it meets this barrier, so you can't have a big avalanche. Well, all that will happen as you keep dropping sand in, eventually it will build up behind the barrier, and then you'll be back to the critical state, and then they can get over the barrier, and you'll be back to just the same situation as before, having a power law in the sizes of avalanches, and you can again have huge avalanches occur. So the measures taken within social systems or even natural systems to prevent catastrophes may be doomed to failure, because the system will always just adapt and evolve around them back into that critical state, which is a robust state. This has been suggested as a problem with fire prevention in forest fires, that if you prevent the forest fire, all that happens is that the forest builds up more and more combustible material, and eventually the fire will happen anyway and will be devastating. So again, the forest tends naturally to evolve towards a situation where forest fires can occur. If you prevent it, then it just makes it increasingly likely that a fire will occur. Again, I should say that all these things are not facts, but these are ideas. So, and as to what might be going on, some people do have that opinion that this is a good explanation of that. Other people are more critical of it, particularly, for example, all these things where I said there kind of can be power laws, even earthquakes or biological extinctions. The power laws, yes, there are power laws, but they're not perfect power laws. And in fact, even the sand pile, either the physical sand pile or the computer model, what comes out of those is also not exactly power laws. So they're close to power laws, but so whether they are really good examples of self-organized criticality, whether they're good examples of critical states, is also at issue. But it's nevertheless a powerful mental picture. So it's not necessarily a one-stop solution. We aren't going to say, wars are explained by self-organized criticality, that's it, you know, we've now explained them. But it's an ingredient of our thought. It's a part of our mental toolkit for thinking about this phenomenon, and we can see the extent to which self-organized criticality may help towards explaining that. And if we have this idea from here that big events don't need big causes, then, you know, it may stop us falling into some naive traps if we go around assuming that big events always need big causes. Now we know about self-organized criticality, we won't necessarily assume that, and so we you know, may be better equipped to deal with what's really going on rather than you know, having naive assumptions about it. Okay, our next topic is that of dragon kings. So we've seen that, as if found in the case of cities, that if we look at the city populations, city sizes, against the log of the rank size plot of cities, we often find a power law. Ziff found that there were power laws in the sizes of cities on a rank size plot. But if we do such a rank size plot for Britain, what we find is that we get London way up here, and then the second city, Birmingham, is down here, and then after that we do tend to get kind of a straight line power law. But London doesn't lie on the same line as the other cities of the country. It's way out on its own, and this is a dragon king. That's London, I should say. Strictly, the definition of a dragon king is when, in a system of elements like cities, one element has more than 70% of the total. Now, some Russian researchers have looked into modelling the idea of dragon kings, and we'll just discuss that in a moment. And they've suggested several reasons that can produce dragon kings. Let's say causes. One of them is the capital city effect, like we're seeing here with London. So what seems to cause this is that London, as a capital city, is not just part of the economic system of Britain, of the UK, it is part of the economic system of the whole world. So it has a role within the world as a whole. If the UK were isolated from the rest of the world, then London probably wouldn't be so large, and it would lie on a power law with the rest of the country. But because it participates in this more global economic system, it gets its population and its wealth from the world as a whole rather than just from the UK. So and then that, you know, that may apply in other ways, in other kinds of systems, but there's it's that the element that is the dragon king is has got a role within a higher level system than the system that you're examining, and it's its role in that higher level that causes it to be kind of lifted out of the system that you're studying to have a much higher value, size, property, whatever it is that you're looking at. Another cause is, I suggest, is mergers. So it's something that may be temporary, and they give the example of Alexander the Great building his empire. He conquered the Persian Empire, and so he absorbed the whole Persian Empire into his own. So his empire grew dramatically by taking over an existing empire, but it was only temporary. After Alexander's death, his empire split up between his successors, and into smaller empires. So, but when you see a dragon king, it may be the result of something like that. Something has taken over something else. It's kind of swallowed a huge thing, and so it's temporarily much larger than it would naturally be. But what will probably come after that is it will then either fragment or divest itself of what it has swallowed. And a third possibility is an overstressed system that's subject to self-organised criticality. So it's like the sand pile. Somebody has come along and piled it up above the critical state, and so it's really poised for a big event. So the next event you'll see will be particularly outstandingly large. It won't be part of the normal power law that you would expect. So the system has been put in an excessively stressed state, and it then has to release all that to get back into the power law condition. So these are some possible explanations for why we see dragon kings. And these Russian researchers then develop a model to explain the origin of dragon kings. And their model is based on a system where people can influence each other's behaviour. So it's a kind of thing that occurs, say, for example, in religious conversion. People who have converted to the religion may influence other people to convert to the religion. Or it can happen in the stock market. If people start selling off a share, then other people are influenced to sell off the share themselves. And it might also occur, for example, in wars. If somebody's fighting a war, some people join in and become allies. Other people might also be influenced by their alliances to join the coalition that fights the war. So their model is based on this idea that people can influence each other's behaviour, and they have three parameters that describe that. R is people's tendency to respond to others. So if person A is trying to influence person B, how likely is person B to be influenced by that other person? How likely are they to respond and alter their behaviour? The next parameter, C, concerns sort of connectedness, the number of connections that people have. So, how many other people are they able to influence? And the last parameter, D, is forgetting, let's say. So somebody's influenced your behaviour. How lasting is that? You may forget that influence after a while and revert to your normal behaviour if you hadn't been influenced. So D measures that, the tendency to forget and stop being influenced after a while. And they find that the behaviour of their model depends on a parameter they call G, which is a combination of these. So it's just the response times the connectedness divided by this forgetfulness or forgetting parameter. When G is large, that's when people influence is strong, because people are highly connected and people tend to respond to influence. and D is small. The tendency to forget is small. So the higher G, the more kind of influence that is taking place. And the model kind of works like a percolation model, so that when G is small, it's like a low probability in the percolation model. So you don't fill in many squares. But when G is very high, it's like a large probability in the percolation model that you fill in a lot of squares, almost all of them. But in between, you can get in a critical state where you'll have patches on all sides, of all sizes. So the Dragon Kings emerge when G is high. So that's like in the percolation model, very high probability, you just get one large connected patch. But if G is lower than that, you can get power laws. And if G is too low, as in the percolation model, you get just isolated patches and a typical size to those patches. So they suggest then that when we see Dragon Kings, they don't necessarily need like a special explanation, that Dragon Kings are kind of a natural property of systems that can also produce power laws or normal distributions, just depending on the value of this parameter G, which in turn depends on these three things. And we could also notice here that we've again got something similar to Ziff's idea about unification and diversification producing power laws, that response and connectedness are like unification. They tend to make people act in synchrony. Whereas D, forgetting, is kind of more like diversification. It's making them tend to act more independently. So, it again gives some sort of extra sort of weight to this idea of Ziff, that the power law occurs when these are in balanced, and when unification becomes dominant over diversification, you'll get a Dragon King in this model. In Ziff's idea, it's just you get a steeper power law, but here they find that you get a Dragon King, excess unification in one of the elements. And this idea of Dragon Kings, the researchers suggest their model explains the emergence of Dragon Kings that you get, for example, in search engines. So that back in the 90s, there were many different search engines. So the share of the market of the leading search engine was fairly low, but then starting in the noughties, it suddenly increased, and you got a Dragon King, which is of course Google. So in search engines, the share have approached 100%, and you've got very few other search engines. So you have so they suggest that we can understand this emergence of a Dragon King as in their model changing the parameter G. As G increased, you went from a power law distribution with search engines of varying popularity to this single Dragon King dominating.